Welcome to all of you in the first session of Mathematics Olympiad Camp. This Bose Maths Olympiad, Winter Olympiad is coming up on November 1. You can register yourself at cheetah.com. We will be starting with this training camp this week, and then we will repeat it for the next few weeks. This is also good for PRMO, RMO, and all those things. So if you're preparing for that, this is a good place to start it. Now, we will be starting with geometry, and let me tell you, this is the senior version of our training camp. So you will be hopefully you are in class 9, 10, 11, 12 or more. If you are a junior student, then you should have attended the 7 o'clock or the 6 o'clock sessions. We will be discussing something called transformation geometry. In fact, we did something very similar in the previous session, but in this particular session, we will be doing a different sort of transformation geometry. Those who have not studied geometric transformations before, let me explain what it is to all of you first. It's a very simple thing. It's a machine, it's an input-output machine which takes in input position or the initial position of the point, and gives out the final position. So its transformation means you are actually moving points on the plane. And the input position is the thing that you put inside the machine. You do the transformation, and the output position is the final thing that you get. There are varieties of geometric transformations which are very important in Mathematics Olympiads. They're important for ISI entrance, CMI entrance, and other sorts of things. So they are very interesting objects to study. One example of geometric transformation is translation. We studied that a little bit in the previous session. There are other geometric transformations such as rotation, reflection, and inversion. And then there are even other geometric transformations which are also very useful in the long run. So they're like glide reflections and so on. There are particular problems that people can do using these transformations, and we will actually start with one such problem. In general, in a common course, you would first learn the theory and then you will go into problems. But in this sort of courses, you should first start with the problem and then backtrack into the theory. I think that's more interesting as well. So let's see how we can learn something about rotation using a problem. We will be using a problem and we will try to learn about the geometric transformation of rotation. Rotation is very simple. You take a point O, which is called the center of rotation, and then after you take a point O at the center of rotation, you take a point P, which is the rotating point, and you sort of move OP, keeping O fixed. So move OP, keeping O fixed. That's what rotation is all about. It's very simple. We have all seen rotation. take a point O, move OP such that you push OP so that P sort of moves in either clockwise or anti-clockwise, and the motion of motion of P is known as rotation. So we will be doing a little bit of, as I said, we will be doing a problem. We will be directly going into a problem to apply this notion of rotation so that we can learn more about it. Okay. So it's very simple. The problem is like this. You start with a triangle ABC. And many of you have seen this problem maybe. And you draw equilateral triangles on two sides of ABC. You draw equilateral triangles on two sides of ABC. Let's call this AMC and ANC. AMC and ANC, A and B. So AMC and ANB are equilateral. Okay, great. So we have two equilateral triangles like this. We want to show that BM is equal to CN. That's our goal. Show that BM is equal to CN. This is goal. This is what we want to show. But we don't want to show this using regular geometry methods. We don't want to show this using regular geometry methods. So prepare your mind to think about this problem in a different way. We will be using rotation to prove that BM is equal to CN. We will be using rotation to prove that BM is equal to CN. ABC is any triangle. ABC is any triangle. Okay. Now, how do we do this? Now, the clue is you have to use rotation. One good thing about rotation is it preserves sizes. So this is something to keep in mind. A rotation is an isometry. A rotation is an isometry, which means it preserves sizes. Whatever was the initial size, the final size is the same thing. So if you can show that CN can be rotated to BM, CN can be rotated to BM, then you would be done. So this is the goal. Show that it is possible to rotate CN such that it falls on BM exactly. Okay, so now Tejas Kulkarni has a very, very good point here. You see, no rotation. He says no rotation about a vertex. What does that mean? Well, he is automatically thinking, and this is something that Raghav Goel is also thinking, that what is the center of rotation? It's a very good question to ask. You see, whenever you want to use rotation, you have to think, what is the center of rotation? That's the first question. So you want to rotate BM such that it falls on CN. But even before you do all of those things, you have to ask about what point this rotation is happening. About what point this rotation is happening. What is the center of rotation? So can any one of you tell me, first you have to think, of course, think and then tell me, what would be the proposed center of rotation? Okay. Raghav and Madhu Mahesh are suggesting that the center of rotation is A. That's their suggestion. Sorry, what are you saying?
Sir, enter PM and CN, intersection of PM and CN.
Okay, some of you all actually said center. What is your name? Sorry, I don't see your name here. Who is this?
Sir, allow me to-
Okay, so this point is suppose O. So he's suggesting that O is the center of rotation. Maybe it is. Alokik theory. Okay, Alokik is suggesting that the center of rotation is O. Audrija is saying that the center of rotation will be between B and C.
Sir,
Yes.
so what? Can't we superpose? Like, can't we just coincide M with C? If suppose M is the center of rotation, then we can bring M to C, right? And then we can bring B to M.
So you have to be very careful about it. Center of rotation is the only point in the plane that does not move. Remember, what are you trying to do here? You are trying to send Cn to Bm. So maybe C goes to B, N goes to M. Or it could be C goes to M, N goes to B. Whatever happens, these points move. These points change their position. You cannot, the center of rotation cannot be a point which does not change its position. It needs to change its position.
Okay, sir.
I'm sorry, the center of rotation, what I mean to say is center of rotation is a point which will not change its position, but these points need to change their positions. So you have to be very careful about it. Okay, so actually Raghav and Madhu Mahesh have already, sorry, go ahead.
Can we rotate triangle ABM so that B coincides with N and M with C at point A?
Okay, actually that suggestion is very good. So Raghav and Madhu Mahesh also suggested this, that let A be the center of rotation. In fact, that is correct. A will work. A will work really well as the center of rotation. But now you have to justify how this rotation is happening, through what angle, and why BM will exactly fall on CM. Why BM will exactly fall on CN. So I gave you the next hint, that the center of rotation is A. Right, Raghav, that's the good intuition, that A could be the point, because A is sort of outside these moving points, which is great. That's true. So now the question is, can we logically establish that it will absolutely work? How do we establish that even? So everyone think about it. Take your time and think, if A is the center of rotation, then how can we make sure that BM exactly falls on CN? How can we make sure that BM exactly falls on CN? It will fall on CN, but why? And what is the angle of rotation? What is the angle of rotation that we are working with? So those who are joining a little bit late, let me explain to you what we are doing. We are using geometric transformations to solve problems which are Maths Olympiad caliber problems, or ISI or CMI entrance caliber problems. Beautiful problems, geometry problems that can be solved in a non-traditional way, using transformations instead of using a bunch of theorems. Usually when we get geometry problems, our intuition is this, okay, our instinct is this, let's use a bunch of theorems and everything will work out. Okay, that sometimes works, but if you go a little bit deeper into problem solving in geometry, you have to think about transformations, you have to think about movement of objects, because that's what's happening at the fundamental level. Okay,
So can I suggest one thing?
go ahead.
Sir, this basically what you're saying is absolutely correct, sir. A is the center of rotation. So, sir, basically ABM will actually coincide with MCN. So, sir, in these two triangles, we can see that
ABM
AM
will
is equal
coincide, will it is, okay,
to
right, yeah,
CMN, and
okay.
sir, here we can see that AM is equal to CM, right? Because equilateral triangle.
Ah, excellent. So AM is equal to CN because the triangle is equilateral. This triangle right here is equilateral. Excellent. What is your name? Sorry,
Sir, Kostav.
Kostav. Okay, Kostav is saying that AM is equal to AC because, oh, sorry, did you say CM? It's actually equal to AC.
Yes, sir. Sir, basically it will be equal to AC. Yes, sir. All the sides are equal. Yes.
Yeah. Okay. So how can we use that here?
Sir, I'm thinking like if we just rotate this triangle ABM, like we have to assume that if we assume that it is like coinciding with the triangle, then sir, we can see clearly that AB will be lying on the line of MN. So if you just rotate it, like BM will fall on CN, AM will actually super coincide with
Wait,
CM.
BM will fall. Okay, okay, where will AM fall?
Sir, this AM will fall on CM. No, look at the triangle of sir, this one.
So it will
and
fall on
CM.
AC.
Okay, someone else said AC. Who is that?
Oh yes, sir. Sorry, sir. AC.
Yeah,
Sir.
it is.
Yes, sir.
Okay,
AC.
yeah, AM will fall on AC. Great, yeah, that's
Yes.
true. Yeah. Where will AB fall?
And,
So if it will fall on
Sir, AN.
yes, sir.
AN.
AN.
AB
sir, it
will
is
fall
true
on
also, no?
AN. Excellent.
AN.
So what is
Yes,
the
sir.
angle of rotation then?
So 60.
Angle of
because
rotation is exactly very good. It's 60 degree. Do all of you see it? About
Yes,
A,
sir. Equilateral triangle. Oh yes, sir.
about A, you have to turn by 60 degree, and AB will fall on AN. Why? So, okay, just for fun, in your mind, think about the trajectory of B. Forget about all those theorems for a moment, okay? Just in your mind, think about the trajectory of B. You will see B will sort of go like this, sweeping like this, like a arc of a circle, right?
Yes, sir.
And M will be sweeping like this to C. And in your mind, you can see this BM sort of turning like this and falling on CN.
Yes, sir.
Do you see that, all of you?
Yes, sir.
Okay, excellent. So you see the beautiful rotation happening, and the result of it is this, that BM and CN are actually equal lines. Okay, so let's spice it up a little bit. This particular picture has much more consequence than this. I'll draw it a little bit smaller. So this is ABC. And suppose we draw two equilateral triangles. Okay, I'll explain one more time. ABC is not rotating. I'll tell you what's happening. We will have M, and we have two equilateral triangles, and this is N. what we just did is we joined BM, okay, and we joined CN. And what happens here? Well, we rotate AM by 60 degree. Think about it like this. Rotate AM by 60 degree. If you do that, where will M go? Adrija, can you tell me where will M go if you rotate AM by 60 degree? Well, it will go to C, isn't it? M will go to C. Why? Because this angle is 60 degree, so AM will fall along AC. The line AM will fall along AC, but how do we know that M falls on C? How do we know M falls on C? Well, it does because AM and AC has equal lengths. AM and AC has precisely equal lengths. So they will fall on each other, right? Okay. Now, in the meantime, AB is also turning by 60 degree. AB is turning by 60 degree. AB is turning by 60 degree. If AB is turning by 60 degree, B will fall where? Well, B will fall exactly on N. Right? B will fall exactly on N because that's also 60 degree. So this means the line BM, what happens to the line BM? Well, M falls on C, B falls on N. The endpoints tells us what happens to the segment. M falls on C, B falls on N, so BM falls on CN. If BM exactly falls on CN, they must be equal, isn't it? Adrija, do you follow? Okay. Okay. Yeah, it's quite nice, isn't it? Okay, let's make it nicer. Let's make it nicer. Let's draw another equilateral triangle on BC. Let's draw another equilateral triangle on BC. Let's call this R. This point R, exactly. It's like Napoleon triangles, yes. Okay, exactly the same way we can show that AR is equal to CN. AR is equal to CN. So maybe AR is like this. We can show that AR is equal to CN. In fact, AR is also equal to BM. You can take two triangles at a time and do the same logic. And you can show AR is equal to CN first, and then you can show AR is equal to BM. There is something wrong with this picture. Can anyone tell me by intuition or otherwise what should happen to this picture? How can I make this picture better?
Sir, they will meet at same point.
Ah, exactly. These three lines, I have drawn it deliberately in a sort of a non-coinciding manner. But actually, you are right. These three lines will actually pass through the same point. So, some of you already know this. They are concurrent. The technical word is concurrent. The question is, how can we prove that? How can we prove that this is concurrent?
Sir,
Yeah, one moment. Let me finish the picture. Then go ahead. Now,
so we can draw these three lines and then we can rotate this whole picture as as when we rotate by 60 degree, let's assume that like we only take two lines.
Okay.
Either of these two lines, we take only two lines and then we rotate and then we see that they coincide. This means that two of them have a same intersection point. Every two of them will have the same intersection point. The rotation properties.
Okay. You are rotating what?
Sir, I am saying that let's forget one equilateral triangle and one line of these three lines.
Okay.
And then what we were doing previously, we just go inside these points, right? So BM coincides on CN. So we say that BM and CN have a common point F. Then when we do for AR and PM, then they coincide on the same point F.
How do we know it's the same point? I mean, there must be a marker on that line that sort of tells us that it's the same point. It has to be the same point.
And the same angle of rotation tells.
Sir,
Yeah, go ahead.
sir, we can like if this is we already know that BM is equals to CN, right?
We know that.
We know that. So basically, if we prove that R, like if we just basically prove that AR is equals to BM, then it solves our problem, no, sir?
Well, we already proved that. Just take the other two triangles and the same.
Yes, sir. So we can take this triangle BMR and ARM.
Yes, that's true.
Then, sir, we can like with like RM will be common here.
Okay. Rn is not
And
a
then
straight line, by the way.
Oh yeah. Okay. Yes, sir. That's also the point. Yes.
Rn is not a straight line.
Yes. Yes. Sir.
I mean, may not
We
be
can't
a straight.
apply that.
May not be. Let me not say not a straight line. It may not be a straight line. Then A, B, C has to be 60 degree. If Rn has to be a
Yes,
straight
yes.
line.
Yes, they are equivalent.
So how do we show this concurrency thing? It seems a little bit tougher than usual. So can all of you give this a try? This is not hard. It's actually quite doable. So can all? How do you show that this point A? So you can think of, you have joined AF and FR. I'll give you a hint. If you can show that these three angles add up to 180 degree, then you are done, isn't it? Don't think of AR as a straight line. Think of, you have joined AF and RF. You have joined AF and RF, and F is the intersection point of BM and CN. You have joined AF and RF, joined the segments. How do you show that these three dotted angles, angle AFN plus angle BFN plus angle RFB is 180 degree? How do you show that? Because if you can show that, you are done. There is something peculiar about these angles. There is something beautiful about these angles. Can you tell me what it is? Can you focus? Yeah, take your time. What can you focus on the quadrilateral AFBN? I'll give you a hint again. Let's do this in the style of mathematical circles. Let's try
Sir,
to
I
get
got
the
it,
answers
understood.
from the kids. Yeah, go ahead. Sorry?
Sir, I think that you are saying that if we just construct a circle around AFBM,
Is it cyclic? It's a good question. So someone is suggesting that this is cyclic. Is it cyclic? Can you show that it is cyclic? If you are suggesting it's cyclic, then maybe you can show it's cyclic. Give it a try. I'll give you a couple of minutes time to think about it. In the meantime, let me make an announcement. The next week we will have the Olympiad camp at the same time. In the meantime, if you are attending Maths Olympiad classes at Chinta, then you will have your regular classes. Make sure to do those problems carefully and also attend the internal PRMO seminar. PRMO is cancelled this year, but it has been replaced by another contest in the month of January. So you should also attend the extra sessions for that. IOQM, exactly. There are Thursday sessions on that for the internal students. And anyway, and this one is a very short session. It's a 40-minute session for the people who are attending for the Bose Mathematics Olympiad winter in the month of November. So it's very similar to PRMO. It's like a preparatory mock Olympiad for that. And the people who have appeared for the summer Bose Mathematics Olympiad, they can go to chinta.com for looking at the awardees of the previous Olympiad. And it's not the PRMO one is not a seminar. It is a session for internal students, and it's usually conducted on Thursday. If you don't know when it is and how to attend it, you should ask your faculty member at Chinta. Okay, so coming back to this.
Sir, is AF equals to BF?
So how do you show that AFBN is cyclic? How do you show AFBN is cyclic?
but do we apply Ptolemy's theorem?
What theorem? Sorry.
Like Ptolemy's theorem, like the an plus b, like the sum of the opposite sides of the quadrilateral, if it is
Okay,
equal to the
Ptolemy's
product of the
theorem.
diagonals. Yes.
Actually, this is good that you raised it. This problem has an application of Ptolemy's theorem eventually, but not in this step. This point F is known as the Fermat point, and it has a beautiful property that Fa plus Fb plus Fc is minimal at this particular point, which means that if you take any other point, let's say F1, then this will be less than F1a plus F1b plus F1c. So the point F is a very, very interesting point with reference to this triangle. To prove this fact, you have to use Ptolemy's theorem, but not in this particular step.
The circumcenter.
F is not the circumcenter. No, not necessarily. Not necessarily. Okay, so I think this can be done very easily by most of you. So I'll give this as a homework, and we will meet again next week at the same time, and we will finish it up and continue with geometric transformation a little bit more, so that we are able to solve more beautiful problems. Till then, take care all of you. Good night and goodbye. I'll see you next week.
Thank you, sir.
Thank you.